Hi everyone, here's a new video with exercises on sampling and reconstruction and on modulation, demodulation. So today we'll solve 4 more exercises on these topics and hopefully everything will be clearer to you. I'm Gio, an assistant professor at UPF in Barcelona, and on my channel I upload theory and tutorial classes on signals and systems. So this is the right channel for you to learn the basics very quickly. Let's get started. First exercise for today. We're given a ideal bandpass filter which has unitary amplitude. Okay, it's shown in the figure. We need to show certain properties of the impulse response that corresponds to this filter. Okay, so HBP of j omega is the frequency response, and the corresponding impulse response is HBP of t. Right. So let's get started. I'm going to draw the frequency response once again, and then we can go one by one through the points A, B, and C. So part A basically asks us to demonstrate, to prove that HBP of t can be written in that form. Okay, so A sine of omega c o t over pi t times a cosine. So how to prove that? Well, we can calculate HBP of t as the anti-transform of the frequency response. So just by using the definition, I use the formula 1 over 2 pi, the integral of the frequency response, e to j omega t d omega. And if I just work out all the calculations, which are rather simple and we've seen them before, we come up basically with a sum of complex exponentials as shown in the slide. So we notice that these can be grouped in a convenient way as follows. Okay, I just apply the distributive property, and I find it convenient to express them as you see at the bottom, right? So basically I just group some common factors that I choose for convenience, okay? And then once we come up with this expression, then let's notice that these terms circled in red correspond to a sine, okay? They're equal, as you can see. They're the same term and they correspond to a sine, okay? Of course, divided by 2j, right? So it's the sine of omega 2 minus omega 1 half t. And what about the other terms in blue? Well, these terms are a cosine, okay? The factor 1 half is missing, so it's equivalent to twice cosine of omega 1 plus omega 2 over 2t, right? And then there's another factor, which is 1 of pi t left, which I wrote in green. So basically we're done, because look, we have just proven that the filter, the impulse response of the filter, can be expressed as shown on the top right. So we have a sine of omega co t over pi t. In particular, the value of omega co is omega 2 minus omega 1 half. Okay, and this is a low-pass filter because we know that it's a sinc function in the time domain, and its Fourier transform is a rectangular pulse, which is a low-pass filter, right? And the other term, the cosine, is a modulating cosine. So it's something at a much higher frequency. That frequency, as you can see, is omega 1 plus omega 2 half. So it's a much higher frequency, and it modulates our signal. And the coefficient is simply 2. Right, so let's move on. In part B, we are asked to prove this, that the same impulse response can be represented as a difference of 2 sinc functions, as you can see, or 2 low-pass filters, okay? So how to do that? Well, if we just continue from this point where we've written the sum of 4 exponentials, well, we can group them again into this form, and then you see that this is basically the difference of 2 sine functions that then are divided by pi t. So we've already proven, part B, this is the difference of 2 sinc signals, and in the Fourier transform domain they correspond to rectangular pulses, so it's the difference between 2 ideal low-pass filters which have different frequencies. And in part C of the exercise, we need to show that HBP of t can be written as you see here. So it's a delta of t minus a sinc, convolution, another sinc. So how to show that? Well, we can simply calculate the Fourier transform of that. So let's recall that the Fourier transform of a sinc function, as you see there, sine omega 0 t over pi t, is a rectangular pulse, which is 1 for frequencies smaller than omega 0 and 0 elsewhere. Okay, I can also write as the difference between 2 step functions, u of omega plus omega 0 minus u of omega minus omega 0, right? So if I don't recall that well, I can verify by just doing the anti-transform of this. I apply the definition and I see that the integral simplifies, and the result I get is precisely sine of omega 0 t over pi t. Right. So now that I know that, I can calculate the Fourier transform of the expression in purple at the top right. So I have the Fourier transform of a convolution of two things. So I know that this corresponds to the product of the respective Fourier transforms. So here I do them separately, and the Fourier transform of the top t is 1. The Fourier transform of the first sinc is basically a rectangular pulse, and the same for the other sinc. Okay, it's just that of course they are at different frequencies because the first sinc has a parameter omega 1, the second one has a parameter omega 2. So here's what I get. Now if I want to represent them graphically, to calculate this product and to actually verify that it corresponds to my original HBP of j omega, I do it one by one. I start with the one circle in green. It's 1 minus a rectangular signal, so it looks like what you see in dotted green at the top left, okay? And what about the second one? Well, I'm representing the second one in red. This is a rectangular signal between minus omega 2 and omega 2. So when I do the product of them, here's what I get, which is precisely my HBP of j omega. So the next exercise is about some system which implements a demodulation function, okay? So as you can see in the picture, we're giving a certain signal y of t, then we demodulate it and filter it, okay? So we need to show, for example, that when the value of phi is non-zero, okay, so in the cosine that multiplies, that demodulates y, there's a phase phi, okay. When this is non-zero, we need to show a certain relationship for part A. So let's start with that. How to do that? Well, I recall, as the exercise tells me, that y of t is some original signal x of t modulated at a frequency omega c, okay. And then I know from the picture that w of t is y of t times the cosine of omega ct plus phi, okay? So I just write this as a function of x of t. Cool. Then I have the product of two cosines, and I recall this very simple formula related to the product of two cosines, which is equivalent to half the cosine of the sum plus half the cosine of the difference, okay? So now if I know this, I can just rewrite this simply as follows. Half x of t times the sum of two cosines. One is a cosine at a double frequency, 2 omega c t plus phi, and the other one is just a cosine of phi, which does not even depend on omega. It's a constant, okay? Right. So if this is my w of t, I calculate the w of j omega, which is what I need to do in part B of the exercise. Okay, so we completed part A. Now part B asks for the Fourier transform of this. So we have the Fourier transform of a product, which corresponds to 1 over 2 pi, the convolution of the respective Fourier transforms. And this is what I have written at the top right. Cool, now let's keep going. Let's calculate separately the Fourier transform of this cosine. So the Fourier transform of this cosine can be easily calculated if I write it as the sum of exponentials, okay? Then I have that because of multiplication by a complex exponential in the frequency domain corresponds to a shift in the time domain and vice versa. So thanks to those properties, I can quickly write that the Fourier transforms are given by the sum of two deltas, each one multiplied by a complex exponential. So if you just follow the calculation, you see that the Fourier transform of this cosine is equivalent to the sum of two deltas, okay? These deltas are placed at frequencies 2 omega c and minus 2 omega c, okay? And they are multiplied by those complex terms e to j phi, which are constant. They're not function of omega. So now what about the other one, cosine of phi? Well, that is not a function of omega, it's a constant. So the Fourier transform of that is actually very simple because it's cosine phi 2 pi delta of omega, because recall the Fourier transform of 1 is 2 pi delta of omega. Right, now I have all the ingredients ready and I can continue to solve part B of the exercise. So here's the final result. Because I have x of j omega convolution deltas, I know that the deltas just produce a shift of the original signal x of j omega. So here's the final result, okay? I have a shifted version at frequency 2 omega c, another one at frequency minus 2 omega c, and another one with no shift, because the convolution is by delta of omega, so it's just x of j omega. And all of this is weighted with some coefficients. Right, I can simplify this, of course, and I can plot w of j omega as follows. So I have one replica in the middle, which is x of j omega times cosine phi over 2. Okay, this is the replica in the middle. And then I have the two other replicas at double the frequency. Okay, so respectively a frequency 2 omega c and minus 2 omega c. Their amplitude is half, and they multiplied both of them by a complex term, e to j phi, but the magnitude of this term is unitary. So here's my representation. Now in part C, I'm given that omega co is equal to omega b, and I need to plot x hat, which is the signal that I recover after some filter. Okay, so how to do that? Well, here, if I represent my filter is given by equation 1. H of j omega is 2 in a certain support and 0 otherwise, okay? I represented it in red. So if I apply this filter, what I get is only the part in the middle, right, that survives. The replicas are filtered out. So I get the triangular signal in the middle, and this is basically equal to x of j omega cosine phi. And concerning part D, well, I'm asked to do the same in the time domain. So in the time domain, it's really the same thing. So the recovered signal x hat of t is going to be x of t time cosine phi. So basically, it's a very good reconstruction of my original signal. The original signal is just multiplied by a constant cosine phi. So let's move on to the next exercise. Again, now we have some amplitude modulation system. Okay, there's an input x of t, which is band limited, and it's the same one as in the previous exercise. Okay, and then so this is modulated, and then I have a certain filter, and I produce y of t. So let's see what happens in this system. Basically, the exercise wants us to plot h of j omega first of all, which is the filter that I'm given at equation 2, and then v of j omega, okay, which is what is fed into this filter. So let's do that. So we start first of all by recalling the signal x of j omega that we had in the previous exercise. So it was something like this, okay? It was band limited, and in this case I'm told that the bandwidth is 100 pi, okay? So the signal goes between minus 100 pi and 100 pi, okay? Now in part A, I need to plot h of j omega and v. So h of j omega is simply this filter, okay? It has amplitude 1, and it extends between 300 pi and 400 pi, and minus 400 pi and minus 300 pi, okay? Just as I'm given by equation 2. So now what about v of j omega? Well, v of j omega, since v in the time domain is the product between x and the cosine, its Fourier transform is going to be 1 over 2 pi, the convolution of the respective Fourier transforms. So the convolution between x of j omega and the Fourier transform of a cosine of 400 pi t. We've seen this Fourier transform many times. So if you recall, it's given by the sum of two deltas with amplitude pi each, okay, as you see there. So if I just do the calculations, I see that I end up with two shifted replicas of x of j omega by plus and minus 400 pi in the frequency domain, right? So I can represent this, and here's what it is. It's the two replicas with half the amplitude of my original signal. Great. Now let's move on to part B. So in this case, I'm asked to plot y of j omega, which is basically the Fourier transform of the signal at the end, okay? So what is that going to be? Well, that is clearly going to be v of j omega multiplied by h of j omega, which is the frequency response of my filter. So let's do that. The filter only preserves part of the spectrum of v of j omega, and so as you can see in y of j omega, I only have two parts of the spectrum. Basically, the triangular signals have been divided into two parts, have been split up. Okay, now part C. So basically here the exercise makes us notice that the output signal is called a single sideband signal. So why this terminology? Well, it's obvious because now only a part of the band is preserved. Only the left part for high frequencies, for positive frequencies, and the right part for negative frequencies. So as you can see, y of j omega preserves all the information from x of j omega. Okay, the information is still there. Okay, but y of j omega will require less energy for transmission, because of course if you calculate the energy now, this energy is going to be less than having the energy of v of j omega. Okay, so v of j omega has more energy, but the same amount of information. Okay, so basically there's some redundancy in v of j omega. Cool. So now in part D, we should try to recover x of t from y of t. So how to do that? We should draw a block diagram of a certain signal that can recover the original signal. So here's what we do. If you recall from the theory class, we need to multiply again by the same cosine that we used in modulation. So for demodulating, we multiply again by the same cosine of 400 pi t. And what is the result of that? Well, that creates again replicas shifted by plus and minus 400 pi, okay, in the frequency domain. So here's the result. Okay, they're also scaled with a gain 1/2. So you see at the bottom of the slide now that we have created replicas, and this is the result. So the signal at frequency 400 pi goes down at 0 and up at 800 pi. And the part at minus 400 pi goes up to 0 and down at minus 800 pi. So here's what we get. Now obviously we will have to filter somehow, because we want to recover only the central part of the spectrum, which is the original signal. So what we need is a low pass filter that has gain 4, because we need to scale up the gain from 1/4 up to 1. And the cutoff frequency has to be 100 pi to preserve only the central part of the spectrum. So here's what happens when we apply the filter, and here's the resulting signal, which is equivalent to the original one. Great. So now exercise 10, okay, to conclude. So we're giving the same signal, x of t, as before, with a certain bandwidth, which is 80 pi, okay? And we sample it at a certain frequency omega s, and then we reconstruct it with a certain filter, which is given by equation 3. So let's do that. So here is the representation of my original signal, okay? The spectrum goes from minus 80 pi to 80 pi. And I'm told to sample it in part A at a Nyquist rate. Okay, so what is the Nyquist rate? Well, it's double the bandwidth, okay, so it's 160 pi. So the sampling rate Ts is 2 pi over that, so it's 1 over 80. Cool. So what is it that I get by doing that, by sampling? Well, if you recall, sampling in the time domain corresponds to creating replicas in the frequency domain. So if this is the equation of my sample signal, so original signal times a train of impulses for sampling it, then I just recall that the Fourier transform of the train of impulses is another train of impulses, but they are spaced by omega s now and scaled up. So the Fourier transform xs of j omega will be, as usual, 1 over 2 pi x j omega convolution the Fourier transform of my impulse train, okay, which is the other impulse train. So here if I do the calculations, well, what I get is the replicas that I was talking about, okay? So my spectrum x is going to be shifted at frequencies multiples of omega s. So the original one, then one at omega s, 2 omega s, 3 omega s, and so forth, and minus omega s, minus 2 omega s, and so forth. So here's what it looks like, okay? I'm drawing it in purple. This in the case of having omega s equal to 160 pi, which is the Nyquist frequency, okay? So here it is. So we're done for now for part A, okay? Everything looks pretty clean here. Now, what about part B? In this case, the exercise says, now choose a different omega s. Choose omega s equal to 100 pi and do the same thing. So if I do the same thing and I choose omega s equal to 100 pi, it's smaller now, notice. Now the replicas of my spectrum are more packed. They're spaced only by 100 pi, okay? Also, the amplitude is going to be different, but the main point here is that they will overlap, okay? Because now I'm choosing omega s below the Nyquist frequency. So the bandwidth of my signal was 80 pi, so I should choose a sampling frequency of at least 160 pi. In the first case, the green one, I'm good because I chose 160 pi. But in the second case, I'm choosing a frequency that is too low, and I'm going to pay a price for that. So in the first case, I can filter my signal, okay? and recover the original signal. So there's no aliasing here, everything is good, I recover the original spectrum. But in the second case, when I try to filter again, I'm not able to recover the original signal because the replicas overlap, there's aliasing, and therefore there's distortion of the signal. So as promised, today we solve more exercises on sampling and reconstruction, and also on modulation and demodulation together. So I hope this helps you understand these very important concepts, and please keep watching the other exercise and theory videos and subscribe to this channel to know when I upload something new. See you in the next class.